Okay, hi everyone. Happy 2024 and welcome back to the Topos Institute Colloquium. Today we're very pleased and honored to have Professor Robert Paré from Dalhousie University, who'll be talking about the functorial difference operator. So Professor Paré, whenever you're ready.
Okay, thank you very much. And thank you for to the Topos Institute for inviting me to give the colloquium talk. I'm pleased to report on some work that I've been doing for the last few months. I've decided to take a break from double categories for a while and do some of the stuff that is in the back of my mind for some time now. And so I'm talking about functorial difference operator. Everybody, I think, would agree that the category of sets is fundamental in category theory. But it's also a bit boring, which is maybe the way it should be if you're going to use it sort of as a foundation for everything. But if you look at endofunctors, then this is not at all as boring as just the category of sets. So let's, whoops, right, let's see. There. So here is the question that I would like to investigate. What does an endofunctor of sets look like? So if I asked you, just give me, some endofunctors of sets, probably the people in the Topos Institute would say polynomial functors, okay? And so polynomial functors have been around in the air for a long time. Koch wrote a long paper in 2009, which he put on the archive, and he's constantly updating it. And Spivak and lots of collaborators whose names, I won't mention. I apologize for that. There are too many people in all, have done fantastic things, with polynomial functors. Okay. Now, Joyal, for example, might say, well, analytic functors. And so analytic functors are very interesting. They were introduced by Joyal way back in 1981. And polynomial functors are special kinds of analytic functors, but this has a different flavor in some sense, has to do with combinatorics and so on. I'll come back to this later. Now, sort of older guys like me and Ernie Manes might say, well, what about monads? Okay, so monads are monads on sets. So an algebraic theory gives you a monad, and monads on sets give you endofunctors of sets. And Manes wrote a paper here which is very relevant to this. And later on, Javil and Zawodowski wrote something which I'm going to also come back to. And then Andreas Blas, also way back 1976, looked at reduced powers, okay, and he showed various interesting things. One of which was that you have an exact endofunctor of sets if and only if there exists a measurable cardinal. So don't ask me what a measurable cardinal is. Doesn't stick in my mind, but they're very bigger than anything that anybody knows, okay? So what is the structure of endofunctors of sets? So I want to study this problem by taking a functor and perturbing the variable x a little bit and see how f of x changes. So the smallest perturbation I can think of is just adding 1. So here's an example. You take the functor f of x equals x cubed, and you look at f of x plus 1. So f of x plus 1 cubed, then they're going to be triples of elements, and some of them have 3 x's in them. That gives you a copy of x cubed. And some of them have 2 x's and a star. That's the element of 1. And there are 3 different kinds of those depending on where the star is. or maybe there are 2 stars and just 1 x. There are 3 of those. And finally, it might be 3 stars. So these are the kinds of elements that you would get in f of x plus 1, okay? And so if you go from x to x plus 1, f gains 3x squared plus 3x plus 1 elements. So that's the sort of thing that I want to do. And you can't do this for any functor because it's going to involve set difference. And set difference is not functorial, but it is functorial. It's more functorial than you would think, okay? So what you need is the concept of a taut functor. So this goes back to Ernie Manna's, the paper that I mentioned, where he introduced taut functors and in the context of monads applied to computer science, okay? And so a functor is taut if it preserves pullbacks of monomorphisms along arbitrary arrows. Or as he calls it, and I'm going to use the same vocabulary, preserves inverse images. So a functor that preserves pullbacks, of course, would be taut, but I mean, there are other ones, and I'm going to try and convince you that there are lots of taut functors. And a natural transformation is taut if the naturality squares for monomorphisms are pullbacks. Okay, so it's a little bit like Cartesian natural transformations, but quite a bit weaker. Okay, so this is the context that I'm going to be doing this in. Now, there are plenty of taut functors. So polynomial functors are taut, and I'm going to come back to all of these. Analytic functors are taut, reduced powers are taut, left exact functors, of course, are taut because they preserve all pullbacks, and of course then inverse image pullbacks. And a functor from set to set that preserves binary coproducts is taut as well. Okay, so they're closed under a variety of operations, and so here you get a sub-2 category taut of cat, whose objects are categories with inverse images. 1 cells are taut functors, and 2 cells are taut natural transformations. So that sort of summarizes all the different ways that you might compose these things. Okay, so that's that. Now, limits of taut functors are taut. That's just the fact that limits commute with limits, but you have to be a little bit careful exactly where you're doing all of this. So start off, assume that you have a category B that has I limits, and you have a diagram of functors and natural transformations indexed by I. And then if each of the gamma i's is taut, then the inverse image is taut. But I'm not saying anything about the natural transformations that you get corresponding to morphisms of I. But if for each little I morphism in I, then gamma I is also taut natural transformation, then the inverse limit is in fact the limit in taut. Okay, that is that the inclusion of taut AB into cat AB creates connected. Whoops, I forgot to say the crucial thing here. I'm sorry. Non-empty connected limits. Okay, so any limits you will get a taut functor, but it's not the limit in taut. And if I is non-empty and connected, then and if the gamma i's are taut, then the inverse limit is the inverse limit in taut. And so let me just give an example here. If you take 2 functors that are taut and suppose that B has finite products, then the Cartesian product is taut, but the projections are not. I mean, you write it down, you'll see it's not. Or even more basic, the constant functor 1 is a terminal object in the functor category, but it's not terminal in taut. Okay, so these are 2 examples where non-empty connected doesn't hold, but for non-empty connected, limits are taut. Okay, so this is the story about limits. Okay, so now the story for colimits is sort of interesting. So I define here a category to be confluent if every span can be completed to a commutative square like this. Okay, so for every pair of arrows with a common domain, I can complete it to a commutative square. No other conditions. Okay, and I colimits commute with inverse images in set if and only if I is confluent. So I was really happy when I found this, because I haven't seen this anywhere, partly because people haven't been looking at sort of inverse image diagrams as such. I mean, if you want, so this looks a little bit like filtered, right? So filtered colimits commute with finite limits. And if you wondered what the condition is for commuting with pullbacks, it's not this. Okay, it's a bit more complicated. You have to have some sort of uniqueness property in there with zigzag stuff and all this. But for inverse images, it's this here. Okay, so I'm surprised I wasn't able to find any reference to this anywhere in the literature. Maybe it is there. Anyways, and so that means then that the colimit functor going from set to the I to set is taut. Okay, so, and here is the theorem: confluent colimits of taut functors in cat are taut, and the inclusion creates confluent colimits. That means, so the first condition says that you don't have to worry about the transition maps, and the second one, if you have the transition maps being taut as well, then you get a colimit in taut. Okay. So examples of confluent colimits are coproducts, which are trivially confluent, filtered colimits, of course, and quotients by group actions. Okay, so that's that's an important construction. So now polynomials. So polynomial is an expression like this. It's a coproduct of powers. Well, the representable functors, x to the ai is the representable functor at ai, and it's just a coproduct. And so these functors preserve pullbacks, and so they're taut. Okay. But I mean, also because it's a coproduct of representables, coproduct of taut is taut. Okay. And so the morphism of polynomials is a natural transformation, but you can sort of analyze this and see that it's equivalent to giving a function between the indexing sets, alpha, and a family of functions going in the backward direction, the fi's like that. And f is defined as said to be vertical if alpha is an identity, and it's Cartesian if all the fi's are isomorphisms. And so what are the taut ones? Well, the taut ones are those where all the fi's are epimorphisms. So you get more than the Cartesian ones, but not everything. Now, analytic functors were defined by Joyal as species. Is the way he defined it was a functor from the category of finite cardinals and bijections, which I'm calling bij here, into this itself, okay, into bij. But there's no harm in letting it go into sets. He was interested in this for combinatorial reasons, and so he wanted the values to be finite, but you can just define it like this. And then an analytic functor is what you get by taking a conextension of a species along the inclusion of bij into set. And the general formula is with the coend there that I've written down, but you can rewrite this as a colimit of powers of n taken over the category of elements of f. And the category of elements of f is a groupoid, and groupoids are confluent, and so this is a confluent colimit of representable functors, and so it's also taut. So analytic functors are taut. And then reduced powers, I just remind you what they are. A filter is a family of subsets which is closed under finite intersections, so in particular empty intersections, so AA is in there, and it's up closed as well. So you're thinking of the elements of F as being the large subsets of A. And then the reduced power is often defined to be the power x to the a mod two functions are equal if they agree on a large set. But a more categorical way of saying this is that the reduced power is the co-limit of all of the powers over all b's that are in F. Okay, so it's not completely equivalent, these two. There's one exception if the filter is a trivial filter, meaning that it contains all sets, and if X is empty, then the top one is empty and the co-limit one is 1. Okay, so that's the only exception. I think that the correct definition is the co-limit definition. Anyways, that's what I'm going to take. And you can see it's a filtered co-limit of representables, and so it preserves pullbacks, and so it's taut. Okay, so that's that. And I just mentioned here that this is different examples from the analytic functors or polynomials. It's not an analytic functor unless F is principal, meaning that it's just a set of all subsets containing some fixed set, and in which case you just get the power. But other than that, it's never analytic. Okay. Now, monads. So the free monoid monad is a polynomial. It's taut. And the free commutative monoid monad is this thing here that I've written down, and that's an analytic functor, which is also taut. Oh yes, and in that paper where Ernie introduced taut functors, he proved the following theorem, that collection monads are finitary taut monads. And I mean, to me, I always imagined that collection monads are just the finitary taut monads, so it would be a tautology, but that's not how it was defined. Anyways, the finitary taut monads are what are called collection monads. But the free abelian group monad is not taut. And I give an example here. I have sets, pullback of sets where the bottom arrow there from 1 into 2 just picks out the first element, 0, and the downward arrow is a constant one picking out the other element. And so their pullback is empty, but when you apply the free abelian group monad, you get this, which is not a pullback. The pullback consists of all mn such that m plus n equals 0. And, so we have z of those, okay. And so the reason why the free abelian group monad is not taut is explained here in this paper by Javil and Zavadovsky. Finitary monad is taut if and only if it can be defined by balanced equations. And balanced equations were introduced independently in 1967 by Planck. And so these are equations that have the same variables on both sides. And so for monoids, associativity just has the same variables on both sides. But for abelian groups, you have a minus a equals 0. So on one side you have a's, and on the other side you have no variable. So this is this paper by Javil and Zavadovsky has significant intersection what I'm doing, but their point of view and what they were doing is completely different. They mostly consider finitary stuff, and they're interested in monads and operads and so on. Okay, good. So finally, I get here to the definition that I'm the main definition here. Given a functor from sets to sets, I define delta f from set to set as follows. Delta f of x is f of x plus 1 minus, so that's set minus, okay, so it's a complement, if you like, the image of f of x in f of x plus 1. Okay, so this doesn't exactly make sense yet, but let me give a couple of trivial examples. If you take a constant functor, then delta of the constant functor is 0. Or if you take the identity functor, which I'm calling x, then delta of x is 1. Okay, so that's So if f is taut, then delta of f of x is a taut subfunctor of f of x plus 1. So that's the main theorem, is that tautness is what allows you to make set difference functorial. And it all depends on the following trivial, more or less trivial fact, is that suppose that you have a function between two sets A and B. You have subsets, A0 of A and B0 of B, and suppose that f restricts to the subsets. Okay, so you get a commutative square star there. Then f also restricts to the complements, A0 and B0, if and only if that's a pullback. Okay, so this is, it's a triviality, but nonetheless, it's worth mentioning, and it's what everything hinges on here.
I didn't get that. Could you try again?
Oh, this is Siri, who seems to be wanting to get more information. How do I get rid of Siri? I think she's gone now.
No, yeah, okay.
Okay, good. So the difference operator then is a functor that goes from taut to taut. So taut is the category of taut endofunctors of sets together with taut natural transformations. And so you get a functor there, and it preserves confluent colimits. Okay, so as a trivial corollary, delta of a constant times a functor is just a constant times delta of the functor, okay? Because the constant times a functor is a coproduct of C copies of f. And also delta of f plus g is delta of f plus delta of g. So the difference operator is a lot like the derivative. It's a discrete version of the derivative. This is the addition formula for derivatives now for differences. Okay, so but it's better, I think, because we don't just get it for sums, we get it for infinite sums, if you like, but also any confluent colimits, so modding out by a group action or anything like that. So the difference preserves. I should mention, I'm not giving any proofs here. The proofs are all embarrassingly computational. At the moment, I don't have, a really good sort of conceptual way of presenting all of this. I just compute it away, and there it is. Okay. Now, the Leibniz rule for derivatives, the derivative of a product, for differences, it takes this form here. The difference of a product of two functors is the difference of the first times the second plus the first times the derivative of the second plus the difference of the first times the derivative of the second, the difference of the second. So this is, if you write this down for functions from R to R, it's a triviality, and it's not very complicated here. It's just set theory. Okay, it's not hard, but that's what it is. Now you could easily imagine if I take three functors, you apply this twice, and then you're going to get something which has 7 terms there. And in fact, you can do this just for any set. You take any product, infinite product or whatever, of functors, of taut functors, and the difference is given by it's a generalization of this. Okay, it's a sum over all proper subsets of I of the product of the FIs for the FJs for the J's in that set, and product of the delta FKs for the K's not in the set. Okay, so it's just generalizing that. And then for non-empty connected limits, delta preserves them. So this settles the whole question for limits, because every limit is a product of connected limits. Okay, so we know now what this is. Now let's look at some examples here. The polynomials. So delta of x to the a, you can just write this down. It's again, it's set theory. Okay, it's just you look at functions from a into x plus 1 minus and so on, and what you get then is that it's a sum of powers of x again, summed over all proper subsets of A. So if you take a polynomial functor, then delta of it is also polynomial. And you can actually write down exactly which polynomial it is. It's again powers, and it's indexed by the disjoint union of all of the proper subsets of all of the AIs. Okay, so I've written it there like that. Now, if instead you take A to be a finite cardinal, then you can group like terms together. Okay, so this B proper subset of A corresponds to there's n choose k of them for k, and it's a sum here like this as I've written down. And so now if f is a power series functor, so this is kind of special kind of polynomial functor where the powers are finite, then delta of f is also a power series functor, and then you can just write down what the coefficients are, and when you just do some simple arithmetic, you get that it's what I've written down there. Okay. Now, for analytic functors, delta of an analytic functor is also analytic. And if the functor corresponds to its species f, then we can also calculate what the species corresponding to the analytic functor is. So it's the species is g to the n, given by the following coend. So I'm taking the coend now over non-empty finite cardinals and bijections. Okay, so n is fixed here, and I let k run through all the non-empty cardinals and take the coend there. So just maybe that's a little bit mysterious, but a G structure then, so the species are species of structure, right? And so a G structure of cardinality n consists of an integer k and an equivalence class of F structures of cardinality n plus k. Two structures like that are equivalent if one can be transformed into the other by a bijection on the k's. Okay, so that's this is so the difference operator applied to analytic functors is analytic. And reduced powers, it's a similar story. If you have a filter on F, it determines an equivalence relation on the subsets of A. So two subsets are equivalent if A and A, it's any A is either in both or in neither. Okay, so A and B if and only if A is in C. And I can write that the B prime and C prime here are the complements of B and C in A. Okay, so the second formulation doesn't look like it would be an equivalence relation, but it is, and the first one does look as if it is an equivalence relation. And so for any B at all, I can get a new filter. So I start out with a filter F, and so for any F on A, right? For any B in A, I get this new filter on B, and C is contained in B if and only if C union the complement of B is in F. Okay, so you calculate and you see that this is a filter, and then the proposition here is that if you have a filter, FB gives you another filter on B, and the difference of the reduced power is the sum of reduced powers. The reduced powers by these FBs over all equivalence classes B not equal to A. Okay, so you take representatives from one from each class B not equal to A like that, and this is the sum. So in some sense, you could have like reduced polynomial functors, and then delta of a reduced polynomial functor would be again 1. Okay, so this I haven't seen, I didn't write this down because I've never seen anybody use reduced polynomial functors. Okay, so this now So good. For the difference operator for functions on the reals, there's no real chain rule. Okay, if you look in the literature, they say, oh, you do this or that and something, but there isn't one. But now we're not dealing with numbers, we're dealing with sets, so we have a little bit more room, and so we can get not a real chain rule, but a lax chain rule. So the lax here is the lax chain rule for taut functors f and g. So I'm looking at delta of g circle f, and the chain rule would say that that should be isomorphic to what's on the left here, delta g circle f times delta f. Okay, but they're not isomorphic, and in fact, even for f and g equal to x squared, but just that they're not isomorphic. I mean, they're not isomorphic for the simplest, simplest functors at all. Okay, so but what you get then is you get natural transformation going from the more complicated thing to delta g circle f, which is monic. Okay, so I mean, ideally we would wish that it would be iso, but anyways, it's monic. It's natural in f and g. So when I said natural up above there, these are functors from sets to sets. So it's natural as functors from sets to sets. But also if I change the f and g, it's natural in g. And it's associative. So I've written this down here, but it's the obvious thing. You take three functors and you look at delta of the composite of the three, and then there are two ways of getting into that, and they're equal, and it's unitary. Okay, so we have a lax chain rule, and so right. The final thing then is we also have something called Newton's series. So given a function from R to R, its Newton series is given by what's written down here. I won't read it out for you. So this is like a Taylor series, but for differences instead. And it's very useful. Like if you want to find a formula for the sum, of the fifth powers of the integers, okay. So you write down the sum of the fifth powers. You take differences. So the next that's going to be the fifth powers, and you take differences again and difference. And after doing this 5 times, then you get 0. And then you just plug it into this and pops out the formula. Okay, so you can use this for various things. So in this, both sides here are just different ways of writing down the same thing. Okay, so the x to the little arrow n are the falling powers. So falling powers sort of are something between factorial and power. It's x times x minus 1, and you take n, keep going down n of them. And x choose n is more or less the binomial coefficient, except that it's an x in there, not an integer. It's a polynomial. And delta to the n is iterated difference. Okay, so I've written down some iterated differences here, and you can just guess what the rest of them are. Now, in order, this looks pretty combinatorial, and so there is some hope of getting one, for functors, and that's what I want to do here. So I should try and understand better what the iterated difference is for functors. Okay, so you can write this down, and it takes some calculation, but it turns out then that the iterated difference is easy enough to describe. It's a set, so the nth difference of f, it's a set of all a's in f of x plus n that are not in any f of x plus k for k contained in n. Okay, so that's what the nth difference is, and Sn acts on this as, I mean, maybe it's not completely obvious, but you can let the permutation act on the n there, so that permutes the a's around. And if a is not in f of x plus k, then when you permute it around, it's not going to be either. Okay, so that's Sn acts on it. And so out of this, you get a species. And then you can take the corresponding analytic functor. This looks okay, except that it doesn't work. Okay, so this is not, it won't give you, I mean, what we're trying to do is to get back x. Okay, we're hoping that when we, at least for nice x, we would get it back. I mean, that's what the Taylor series is about, right? Doesn't give x, not even for polynomials, not even, I think, probably not even for x squared, but certainly not x cubed. Okay, it just doesn't work. And the reason is that if you take just, let's say, the functor x cubed, this is a connected functor. Okay, it just has one component. And here you can already see that there are several components there. And in fact, you know, for x cubed, there are a number of them that are non-trivial. So not the right thing. But the delta n of f has more symmetries. I don't know if you want to call them symmetries or not. And it's this, if you have an onto map, an epimorphism of finite cardinals, then f of x plus e, okay, restricts down to the differences. Okay, so again, this is a calculation. You use the proposition up above there, and you can see that. So that for epis, you can act on the differences. So this led me to define the category surge. This is finite cardinals and surjections. So it contains Bij, but it also has the onto maps in it. And a functor from surge into sets I'm calling a soft species. It's soft because the structures can be compressed down. Okay, that's if you have a structure on, you know, with like for example, for connected graphs, okay, maybe you can do that. But if you're looking, let's say, at the set of all group structures on a finite set, then you can't do that. Okay, so this is soft species. And a soft analytic functor is a left Kohn extension of a soft species. Okay, so this is people talk about soft analysis and hard analysis, but maybe, I don't know, it's not the same thing, right? Anyways, this is in 7 is the paper by Javil and Zabadowski. They call these semi-analytic functors. I call them soft analytic functors. And the formula is the same, it's just a left Kohn extension. And now analytic functors are soft. You can make them soft because an analytic functor is a Kohn extension of a functor defined on Bij. And Bij is contained in surge. Okay, so you can do the Kohn extension in 2 steps. So you can extend to surge, okay, and you can write down what the formula is to soften a species like this. And soft analytic functors are taut, okay, because surge is confluent. It's confluent because you can take push-outs in surge, okay. So yes, so we get taut functors. Now let's just look at what an element in such a soft analytic functor would look like. It's an equivalence class because it's a colimit, right, or a coend, consisting of an n and an element of Cn and a function from n into x. And the equivalence class is if you can join 2 of these things using surjections by a zigzag of surjections, okay, between the n's there. And so if you take the f and you factor it, then you see that any any equivalence class ACN has a representative in which the F there is monic. Okay, so the AF, the equivalence class of AF, is equal to the equivalence class of B. I didn't give that a name there, but the map from K into X. Okay, so every equivalence class has a representative, and then there's still some modding out to do to get it. But what you get then is that the C tilde of X is Cn cross all monos from n into X mod Sn, okay, mod the symmetric group on n elements. Or another way of putting it is it's Cn cross X choose n. So X choose n is simply the set of all subsets of X of cardinality n. Okay, so both of these are the same thing, but this is only as sets because mono n X is not a functor, nor is X choose n a functor of X. Okay, neither of them are functors, but because Cn has more structure, then somehow this compensates. Okay, so we'll see how this works out. So now, given a functor from set to set, a taut functor, the sets delta n fx extend to a soft species. Okay, so I sort of explained why that was before. And then you get a corresponding soft analytic functor. And this is the functor that is going to be the Newton series of f. And as sets, what you're getting then is the Newton series of f is delta nf at 0 times the monos from n to x, that's set mod Sn. So this is the same as before, but before it wasn't the delta n, it was just an arbitrary g. And also this other formulation there. And so you should compare this with the original formula for the Newton sum. Okay. Now, Newton sum, of course, for functions from R to R, sometimes will converge to f, and sometimes it won't. Okay, so for polynomials it does, and for power series, but we take a sine function or something like that, won't converge to it. And when it doesn't converge to it, you just give up. But here, once again, we have more room to maneuver. And so here, this is what I'm calling now the fundamental theorem of functorial differences, sort of by analogy with the fundamental theorem of calculus that says that the integral and the derivative are sort of inverse to each other. Taking a soft species and doing the Kahn extension gives you a taut functor. So this, you have a functor from soft species into taut, the tilde there. So tilde is left Kahn extension. And you also have a functor delta star going from taut into soft species by taking differences. Okay. And the theorem is that tilde is left adjoint to delta star. And furthermore, the unit is an isomorphism. So if you start with a soft species and you look at its analytic functor, and then you take the differences, and then you do the Newton sum, you get the soft species back again. And so the corollary then is the Newton sum of a soft analytic functor converges to it, if you like. It gives you that's what force is there. Polynomial functors as well. But I mean, I think it's nice that it comes out as a left adjoint. And so you might say, well, I'm not surprised because the tilde is left Kahn extension, so it's already a left adjoint, which is true, and then sort of that's the basis of it. But you have to do some work to show that it actually restricts to taut functors and taut natural transformations and so on. Okay, so I think basically that's it. I just summarize what I've done. I first of all identified the taut functors as the right context in which to do functorial differences. I discovered these confluent colimits, which are central. I still a bit worried that somebody else did this. I would be glad for reference. Actually, I'm a bit worried that somebody else did everything that I've done, so I've generalized the sum and the product rules for derivatives or for differences to colimits and limits, which I think is a good generalization. And we've established a lax chain rule, which is good, and express a Newton sum as a left adjoint. And I have in preparation here, it's half written up and half in scrap paper here, a multivariable version of this on pre-sheaf categories. Okay, so thank you. And these are the references here.
Thank you. Thank you so much. Thank you, Bob. That was very inspiring talk. I love the build up to the fundamental theorem at the end. And so now we have time for questions. And so here in the Topos Institute Colloquium, we do questions in two different ways. One is that you could raise your hand, and then I'll call on you. You can unmute yourself, and you can ask the question. And then alternatively, if you prefer to type in your questions in the chat, you can do that, and then I'll ask on your behalf. Okay. So I see we have a question from Kevin. Kevin, you unmute yourself.
Yeah. Hi, Bob. Thanks so much for the talk. Really, really interesting. I think this confluent co-limit concept seems so natural. I totally see why you feel like somebody must have had it before, but I hope not. That's great.
Yes.
Do you know whether filtered colimits, coproducts, and group action quotients generate all of the confluent colimits?
It's a good question.
In an appropriate sense.
Yeah, the answer is I don't know.
Sure.
Yeah, I don't know of any other examples, but I haven't. I will think about that. Yes, that's a good. Let me write this down. Confluent equivalent to coproduct. Yeah. Okay. Yes, that's an interesting question.
Yeah.
Should be settled. I mean, it would be interesting if there were other ones.
Right.
Yeah.
Okay, and if that was quick, if I can do a second question, I was curious about this lax chain rule. I guess I mean, you were writing down coherences, right? So you could easily axiomatize, I guess, a sort of endofunctor of a monoidal category that has a chain rule structure on it or something, right? Is this also something that we've sort of never seen before anywhere else, or do you know whether that comes up anywhere else?
Yes, it's something that I haven't thought about and I haven't seen, but yes, no, that's also interesting. It's sort of like derivations where you give, a definition, and then you can use it, to calculate what the derivations of polynomials are and so on. Yeah. Well, that's yes, an interesting question too. Yes, I will write that. Yes.
Lots of great new ideas here. Thanks again.
Thank you. Yes.
Thanks, Kevin, and thanks, Bob.
Thank you.
So we have Valeria. Valeria, I see that your hand is up.
Hi, Bob.
Hi.
Lovely talk, and it's very interesting to see this thing about doing the difference instead of the differential. So my question is about connecting that to the stuff that people are doing on differential linear logic and stuff like that, because I noticed that the balanced equations showed up somewhere too. So have you talked to the guys that did the differential, the notions of differential categories? So Robin Cockett and all those guys about it. I mean, presumably it's difference that becomes differential when you go to when you pass to infinity, right?
Yes. Well, the answer is that I haven't talked to anybody about it. You're the first people I'm talking to about it. And so
Thank you.
The first iteration, of a process here. Well, actually, it's not completely true. I spoke in the seminar here about it, and there was some question about how we could get the derivative, like, so the derivative of polynomial functors, for example, that's a nice useful thing, and or analytic functors. It's a useful thing, but it's defined in terms of the presentation. Okay, it's not like if I give you a functor and you don't know whether it's a polynomial functor or not, then you don't know how to take the derivative, even if it is. Okay, so this is defined just in terms of the functor itself. Of course, since the functor determines, all the coefficients, then you could presumably work it through. But anyways, it would be, yes, it would be interesting to first of all figure out how to get the derivatives out of this here, which I don't know. I don't know how to do. They certainly appear there. Like, I mean, you saw with the x cubed, I have 3x squared plus other stuff. Okay, the derivative is there. That's the same in all of the examples. The derivatives are there, but there's other stuff, and I don't exactly know how to get rid of it by taking a colimit as 1 goes to 0, for example. Okay.
Right. No,
Yes.
it is very, very, very interesting indeed to see all
Thank
these
you.
different examples. Thank you.
Yeah.
Thanks, Valeria and Bob. I see we have two hands up. One's from Bryce and one's from Dana. So maybe Bryce, you could unmute yourself first.
Thanks. Yeah, mine's a quick question. Thanks for the interesting talk. I was wondering if there's a nice notion of a free taut functor on, say, a functor or an endofunctor that you could define.
I thought of that, and I wasn't able to get anything. Yeah, well, yes, that's so. I think not, but well, no, maybe. I mean, there are like free exact functors and so on like that. So yeah, so maybe yes, that's yeah.
Okay.
I thought about it a bit, but I didn't get anything. Yes, it's yeah.
Okay. Thank you, Bryce, and thank you, Bob. I think Dana has a question. Dana, do you want to unmute yourself?
Yes, did I unmute?
Yes,
Am
we can hear you.
Yes, such a nice talk, and sorry for a
Thank
really
you.
dumb equation. If you have all these formulas for taking derivatives, what about solutions to differential equations?
Uh-huh.
Are there some analogies from the calculus where we get interesting functors because there are solutions to some nice equations?
I don't know. That's an interesting question. You know what I mean? There are all sorts of analogies, to pursue. I mean that's definitely an interesting question. Yes, it's but the answer is that I don't know of any examples basically. But yes, right. I can't can't give you any better answer than that.
Thank you.
Thank you.
Thanks, Dana, for your question. Thanks, Bob, for that.
Thank you.
Yeah, Andreas, I think you have a question. You can unmute yourself.
Yes, I do. I hope, actually, I have a comment rather than a question.
Right.
You were worrying that somebody else might have done this stuff.
Yes. Oh dear.
Because I have an example where I proved some stuff, then discovered after it was published that somebody else had already done it. So I had to publish another addendum saying, wait a minute, they did it first. And I still get cited because I'm reference 1 on your slide here. The main theorem of that paper was actually proved earlier by, I believe, Tunkova and Reiterman.
Oh.
And if you look like 1 or 2 volumes further on in the Pacific Journal, there will be a like a one-page paper by me saying, yes, they published it earlier.
Oh, okay.
So I'm just pointing that out, partly as reassurance, partly as setting the record straight. That is strictly speaking not my theorem there.
Yeah. Okay, thank you. I should say that I enjoyed that paper, but I also enjoyed, I just discovered not long, one of your references in there said two closed structures of
Filters.
filters, yes. And I'm surprised that hasn't been around. I mean, those are really nice, especially the G category there, you know,
Yeah.
which and people don't seem to know about this, so people should look this up.
Yes, and I might add that the fact that that's about closed categories
Yes.
rather than monoidal closed or any,
Yeah.
there's nothing monoidal mentioned there.
Right, yeah.
It's an artifact of the prehistoric time when I wrote that.
Yeah.
When people were really looking at closed categories, usually apart from monoidal
Yes.
situations. I think it was Ironberg and Kelly originally had this big paper on closed categories. And that's sort of where I picked up the ideas, and that's the framework in which that paper was written. If I was going to write it today, the word monoidal would occur somewhere in there, I'm sure.
The word monoidal does occur in there,
Oh.
and because you mentioned that it's non-symmetric, and in fact, it's only in one variable that you have the hums, which is interesting.
Right. Yes.
Yeah.
Thank you. Thanks, Andreas and Bob. And I think, given that we have a pretty wide audience here in the Topos Colloquium, and if anyone knows of, you know, if this work was done in the past, please do email Robert about this, and or ourselves, we can forward the message along. But I do think that it's a good sign when we get worried about our work having been done before in the past. It means that this is pretty foundational stuff that should be out there. So thank you, Bob, for sharing all this.
Thank you.
I do have some questions myself, and I mean, a lot of my questions are on the form, like, is this related to X? But I'm going to kind of avoid that. Like, well, so I do wonder if there's a relationship to good witty calculus, but that's not my question that I want to ask. I actually want to go back to your question, your fundamental theorem, and I'm trying to understand it a bit more. When I look at the finite difference operator for functions, and then trying to think about how we can get the original function from the finite differences, then I imagine we will use some kind of Mobius inversion formula to get that. Is that the right way to be thinking about your fundamental theorem? Is there some kind of Mobius inversion going on in there, or you're saying something different?
No, I'm not. It's just computational. It's just set theory. I just look at the sets involved, and you know, I see. Well, right. I mean, it's con extension, and then after that, you have an adjunction for con extensions, and then it restricts down to these finite differences. But there's no Mobius inversion in there. I mean, yeah. I sort of had the feeling that maybe using some kind of Mobius inversion, I could get the derivative out of the differences. But yes,
okay. So the goal of the fundamental theorem wasn't to recover the original functor.
It was, yes, it was. It was to
It
recover.
was okay. Sorry.
It was to recover it, and yes, and it does recover it for good ones. Namely the soft analytic, but yeah. So yes,
I see. Thank you so much.
Could I make a comment about that? Just about derivatives and integrals and stuff. So, as far as I can see, if you take the fundamental theorem of calculus, which says in various forms that differentiation and integration are inverse of each other in some appropriate sense, the finite analog will have finite differences, and I'm talking in the world of numbers, not sets.
Yes.
Finite differences, and the inverse of that is just going to be summation.
Yes.
So it's much simpler than Möbius inversion. And I think the summation that we see in ordinary analysis and so on will correspond to something like the co-ends that you're seeing when you do these Kahn extensions.
Yes, yes, yeah.
Okay.
There's still the question of what is the right analog of Möbius inversion in this context?
Right.
Good question.
Yeah. Well, when you say just summation, I mean it is the formula that I wrote down, right? I mean it's not
See.
that. It's that. I mean that's the summation, right?
Yes. Let's see. I want these x zeros. Yeah. I mean here you're inverting actually an nth. Well, derivatives of all orders.
Yes,
I'm
yes.
just talking about just inverting a derivative as in
Okay. Yes. No, you're right. Yeah. Okay.
fundamental theorem of calculus. So that's much easier. That's just a
Yes.
nice, easy summation. And
Right.
here is what you've got written down here is what you get if you keep iterating that and taking higher and higher differences into
Yes.
account.
Yes. Yeah.
Okay. That was a good discussion. And do we have any more questions from the audience before we end the live stream? Okay. I think that's all the questions we have for the live stream. We're going to go over to our Zoom chat after this. So let us thank Bob again for the wonderful talk, and thank you for answering our questions.
Thank you.
Okay. And I'm going to end the live stream now. All right. See you guys next week.